Hello friends, this video on p-block elements part 10 is brought to you by examfear.com. No more fear from exam. Let's talk about halides now. So group 13 elements easily react with halogens to form trihalides. The exception is my thallium. Thallium iodide, it doesn't form this, but other than that, the group 13 elements, all these forms halides. Boron, aluminum, gallium, they all forms halides, trihalides. And these can be easily prepared by heating this group 13 element. This is my group 13 elements. It can be anything, boron, aluminum, gallium, indium, with some halogen. Halogen can be fluorine, chlorine, bromine, iodine. It forms metal halides. Correct. And please note here the fluorine halides are ionic in nature because of the high electronegativity. We have told that to determine whether a compound is ionic or covalent, we have to see the electronegativity difference, and if the electronegativity difference is high, it's ionic. If it is low, it is covalent. So since for fluorine itself, the electronegativity is very high, so generally all the fluorides are ionic, and since they are ionic, they have high melting and boiling point because the force of attraction is more, right? This we have learned in the past few chapters where we have told about the ionic compound and the covalent compound, and we have told that ionic compound has more melting and boiling point because of the more force of attraction. So if you had doubt in that, you can watch the previous videos where we explained why ionic compounds have high melting and boiling point. So similarly, fluorine, since it is more electronegative, so the fluorides are generally ionic with high melting and boiling point, while other fluorides, chlorides, bromides and iodides, they are covalent, and since they are covalent, they have low melting point. Correct. We'll discuss here bromine chloride. It easily accepts lone pair electron from ammonia to forms BCl3. Why? Because we see bromine has 6 electrons now and ammonia has 1 extra lone pair. So this guy will take this lone pair and form this compound. And see the stage will also defend. This is planar. This is sp2 and this is tetrahedral sp3. Right? The shape will also. We'll discuss more about this in the next few slides. And if you see aluminum chloride, this achieves a dimer shape. This is the shape of aluminum chloride. If you see there are 2 aluminum chloride molecules. This is my aluminum, this is aluminum, this is a 3D structure, this is my chlorine, green ones are chlorine, and this is how the shape of aluminum chloride. We'll discuss more about aluminum chloride and bromine chloride now, the next few slides. Let's discuss the boron the boron chlorides, boron halide. Let's discuss the boron halide now. As I've already told, boron always forms covalent bond. Why? Because small size. So boron halide will always be covalent. Correct? Doesn't matter with which it is forming the bond, fluorine, chlorine or bromine. Doesn't matter. It has to be a covalent bond because boron is small in size. It always forms covalent bond. So boron halides are covalent in nature. Since they are covalent, they are solvent in organic solvent and they are bad connector. And why this happens? This also be discussed that covalents are solvent in organic solvent, soluble in organic solvent. So if you have doubt in this, again you can watch the previous videos where it explain why the covalent compounds are soluble in organic solvent. Right? And this has sp2 hybridization. If you see, it has sp2 hybridization because it has only 3 electrons now, 1, 2 and 3, 3 electrons pair, so sp2 hybridization, and 1, 3, 1.3 is the picometer, is the length of BF bond. Right? This is the shape. This is the sp2 hybridized boron trihalides. It has great tendency to accept electron, as we explained in the last slide. So it is a Lewis acid. Why? Because it is electron deficient. It has 6 electrons now. So it will accept electron from ammonia. So you see the reaction. This is my 6 electrons it has. It has 2 extra electrons. It will accept the electron from ammonia. It becomes tetrahedral. Right? From planar to tetrahedral. This is sp2 and this becomes sp3 hybridized. The best part is this. Please pay attention here. This is the little tricky part. The Lewis acid character decreases in this format. So the expectation is, since the fluorine is more electronegative, the expectation was that this should be more acidic. Right? So if you compare these three, boron is same in all. If you compare not the difference in the electronegativity of boron, chlorine and bromine, it should be that the BF3 should be more acidic. Correct? That should be the case, because fluorine is more electronegative. But that is not the case, because first thing, it is Lewis acid, right? And second thing is because the halogen boron back pi bonding. Well, I'll discuss what is this. Let me write this term. Halogen, and this happens predominantly with boron and mostly with fluorines here. Fluorine has the maximum tendency of back pi bonding. This is the reason for this behavior. So let me discuss this behavior. So now we have seen that fluorine has more electrons. Fluorine is very hungry, right? This guy is hungry. This guy is crying for electron. So what will happen is, since fluorine is very much electronegative, it will share some electron with fluorine. So some electrons will flow from here to here, right? So 2p orbitals of fluorine, they have lone pairs, actually, if you see. So this guy will go to fluorine. So fluorine will become happy now. Correct? Since fluorine is happy, it will behave as weak Lewis acid. Since boron is happy, since boron is happy now with electrons from fluorine, and this is also called the back donation, because fluorine is giving donation to boron. Since boron is happy with the electrons, it will behave as a weak Lewis acid. Because see, the reason why it is behaving as an acid was, it was the Lewis acid, right? It was boron was electron hungry, so it was in need of electrons, so it reacted with ammonia. But in case of this one, since the fluorine is satisfying the need of boron, boron is happy. So this boron is happy in this case, right? In this case, this boron is little okay, and in this case, this boron is little sad, because the bromine is not satisfying the need of electron deficient boron, but fluorine is very well satisfying the need of electron deficient boron in BF3. So this boron is happy. Since this boron is happy, it won't act as Lewis acid because it doesn't need electron now. It's already happy. So it's, as I told, right, all the elements, the way they react, all depends on the stability. They want to be happy in life. They want to be stable in life. So boron wanted electron. It was deficient of electron. Fluorine was a little kind, and fluorine gave the electron to boron. Boron is happy. Since this is happy, it won't act as a strong acid. But in case of BBr3, this boron is not happy because this is not getting electron from bromine. So it will act as a strong Lewis acid compared to BF3. Correct? And please note, fluorine is most kind as compared to chlorine and bromine. So this back donation occurs more in fluorine. Correct? Because the size of fluorine. The size of fluorine is less. So the back donation occurs more in case of fluorine. Hope you understand this concept. So since it was a Lewis acid, it was all the hungerness of bromine that determined the acidic nature of boron halides, right? It was all the hungerness of boron, It was all the hungerness of boron that decides the acidic nature of boron halides. In case of BF3, the boron is happy with the electron donation, back donation from fluorine. So it is not a strong Lewis acid. In case of boron bromide, the boron is not very happy because the bromine is not giving enough electron. It is sad and it is unstable, and it is strong Lewis acid. So let's see aluminum halide now. See, aluminum halide forms a dimer structure, as I told, at a temperature below 473 Kelvin. See, if you see aluminum structure here, right? If you see this aluminum here, so I have Cl here, I have Cl here, I have Cl here. One more aluminum, let's suppose I have Cl here, I have Cl here, and I have Cl here, correct? So now if you see, this aluminum is not happy because it has 6 electrons. 2 plus 2 plus 2, 6. This is also not happy because it has 6 electrons. So what this guy will do, this guy will form a bond with this chlorine. So it will get 8 electrons now. Correct? And this guy also will form a bond with this electron, chlorine. So this guy will also 8 electrons. So now this is happy, this is happy. Both the aluminum is happy. So that's why it will form this dimer structure where this length is 206 and this one which I have extra, right? This is 2 to 1. and the angle is 118 degrees, this is 79. This is the structure of aluminum halide, and this is the three-dimensional structure. Now the question is, why boron is not forming this curve? When boron also has the same issue, right? As if you see BL, when we see the BlCl3, boron has the same issue. If you see boron, I have chlorine here, I have boron, same issue with the boron also, right? What we had with aluminum, it has, for example, it has BCl3 6 electron, it is BCl3 6 electrons. The same issue. Why boron is not forming this bond? Because boron is very small in size and it cannot handle 4 chlorine molecules around it. See, in this case, boron is the main guy, right? Boron is the one which is handling. Here, aluminum is the one which is playing the critical role. If aluminum, if the central atom itself is very weak, how will it hold 4 atoms? Here, the boron is very small in size, right? So it cannot handle 4 chlorine atoms around it. So BCl3 is not forming dimer shape. Hope you understand this. The next question is, AlCl3 is dimer but not BCl3. The same thing which I explained. In case of aluminum, if you see, I will discuss once again, little difficult concept. I have aluminum in this fashion, right? Deficient of electrons, both electrons, aluminum has 6 electrons. It will form a bond with this and form a dimer structure. But when you talk about boron, right, it also has the same problem, but this will not be able to form bond with chlorine because this boron will not be able to handle 4 chlorine atoms around it because boron is so small, it's not able to handle 4 chlorine atoms. A good question is, why BS3 exists but not BCl3? Think. See, the last question we solved was that AlCl3 and BCl3. We talk about the size of the chlorine, right? The size of the chlorine was something which was responsible for not existence of BCl3. But why BS3 exists then? Think. You'll see that the hydrogen size is less. If you compare the size of boron, hydrogen and chlorine, this is the size. Correct? So if you see, and you see BCl3, boron will not be able to handle 4 chlorine atoms around it. So BCl3 won't exist. But BS3, yes, it can, because boron can handle 4 hydrogen atoms. And the shape is almost similar to what we have for AlCl3, dimer shape. So here also if you see BS3, if you form the BS3 shape, this is my boron, this is P, this is H, and this is H. One more boron if you form, right? So this boron has 6 electrons, 2 plus 2 plus 2, this is also 6 electrons. They are both sad, right? So what they'll do, they'll form a bond like this. And now both will become happy. Correct? And thus it will form this kind of structure, dimer structure. This is my boron, this is my boron, and now all the white ones are hydrogen. Correct? Now, thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.